I'm going to start this video by talking about the different quantum numbers that represent the address of an electron, and then eventually we'll get into electron configurations, and more specifically for this video, we'll learn how to do orbital diagrams. Okay, so we're going to start here with some quantum mechanics. Basically, there are four different what we call quantum numbers that can represent the address of an electron. So if you were trying to find an electron to figure out where it's at, we already know according to the quantum mechanical model of the atom by Schrodinger that we don't know exactly where an electron is located. So this is just us trying to figure out more information about where these electrons are. And there's four numbers that would give us the address of an electron. Again, we don't know exactly where they're located. It's all probability based, but we're trying to get some more information here. So that's what we're going to look at initially here. The first quantum number is called the principal quantum number. We use the letter N to denote the principal quantum number. This is the energy level. If you remember when we were going through the Bohr model of the atom, we talked about how N represents the energy level. So the principal quantum number is the same thing as an electron's energy level. All right, these are just the areas around the nucleus where you're going to be likely finding electrons. So if you want to think about the Bohr model of the atom, it's kind of like the orbits that the electrons have. Those are your energy levels. Now we know the Bohr model of the atom is not, 100% correct, but it does help us understand a little bit more about the atom here. So these energy levels and the principal quantum number tell you a little bit more about how close an electron is to the nucleus. So the principal quantum number can go from 1 to 7. 1 would be the lowest in energy and closest to the nucleus, and then 7 would be the highest in energy and furthest from the nucleus. So if you look at this picture, imagine the nucleus is here in the center. The first kind of ring outside the nucleus, that would be your first energy level. It's the lowest number, and it's the lowest in energy closest to the nucleus. And then you get the second one, the third one as you go out, and so on. So the principal quantum number goes from 1 to 7. So anytime you see N, you need to think principal quantum number, energy level here. A little bit more about the principal quantum number. The lowest in energy, we already said, is when you have N equals 1 right outside the nucleus. This is what we call ground state. And then excited states are anything higher than that. So energy level 2, 3, 4, so on. All right. So electrons in these excited states are further from the nucleus. They have, larger paths around the nucleus. So that's why they have a higher energy. If you want to figure out the maximum number of electrons in any energy level, just use this simple little formula, 2n squared. So n represents your energy level. If you're in the second energy level, what's the maximum number of electrons that there could be? So 2n squared. 2 squared would be 4 times 2 would be 8. So the maximum number of electrons in the second energy level, where n equals 2, would be 8. So you just got to remember that you can use this simple little formula here, 2n squared, to find the maximum number of electrons in any energy level. If you don't have your periodic table out, it's probably a good idea to get your periodic table out, maybe pause the video, grab it, because you need to label this stuff so that you can see this for future reference. We're going to be using the table a lot with this, and the table can give you a lot of information for electron configurations. So if you notice on the left side of your table, there are numbers. It goes from 1 to 7. If you look closely there, these rows are all labeled 1 through 7. What I would do is I would point at those numbers and label them N and label them energy levels. The energy levels are the rows on the periodic table. So if you're in the second row, you're in the second energy level. All right. So these two rows at the bottom, they don't get a number because technically these two rows go in the 6th and 7th row here. So those numbers on the left side of your table, they represent your energy level. They represent the principal quantum number, or N. So if I said, what's the principal quantum number of beryllium? Beryllium's in the second row here. He would have a principal quantum number of 2. So make sure you have that labeled on your table. The second quantum number is called the azimuthal quantum number. And this is denoted by the letter L. And this is talking about the shape of an orbital. We'll talk more about an orbital in a little bit, but this is representing the shape here. So the basic idea is that you have these energy levels, which are areas outside of the nucleus where you're likely to find electrons. They are divided into sublevels, or what we call subshells. All right, so energy levels can sometimes be called shells. So we divide those energy levels into sublevels or subshells. So these are just areas inside an energy level, all right, where you're likely to find electrons. So every energy level can have several sublevels with different shapes. And all this is just talking about areas where you're likely to find electrons. So the sublevels or the subshells are denoted by letters here. All right. Technically, there is a number associated with this, as we'll talk about in a little bit, but we oftentimes talk about these specific sublevels with letters. And the letters we use are S, P, D, and F. So anytime you see us talking about S, P, D, or F, we are talking about sublevels. These are areas inside the energy levels that are where you're likely to find electrons. As you go from S to P to D to F, you're getting more and more energy. All right, so S would be the lowest in energy, and F would be the highest energy sublevel. So anytime you hear azimuthal quantum number, you want to think about these sublevels and these letters S, P, D, or F. Each of these sublevels has specific characteristics about them that you do need to know. So we'll start with the S sublevel here. The S sublevel has an L value equal to 0. Remember, the azimuthal quantum number does have a number associated with it. Even though we're going to be talking about it most of the time with the letter S, technically this is a number. There's a number associated with that. So the azimuthal quantum number of an S is 0. All right, so anytime you're asked for an azimuthal quantum number, you need to figure out first if it's S, P, D, or F, and then you can say, well, if it's S, the L value or the azimuthal quantum number is 0. S's can only hold at most 2 electrons and no more, and the shape of an S orbital is spherical. You don't need to be able to draw it or anything like that. Just knowing that the shape of the S is spherical is good enough. All right, so the next sublevel here, P, has an L value equal to 1. All we did was increase the value, so we went from 0 to 1. P's can hold at most 6 electrons, and the shape of the P is a dumbbell. Again, you don't need to draw it. You just need to know that the P has a dumbbell shape. And then as we go to D, the L value increases again. D's have an azimuthal quantum number or an L value of 2, and they can hold at most 10 electrons. The shape of a D is a double dumbbell. And then the F sublevel has an L value equal to 3. It can hold 14 electrons at the most, and its shape is crazy. We don't care about it. So the key here is you do need to know this information about these different sublevels. You need to know their L value. You need to know how many electrons they can hold at the most and their shape. And I know right now you might be thinking like, oh my gosh, how am I ever going to remember these numbers, like the L values and the maximum number of electrons for each of these? You'll see that this all ties together here with the periodic table. There will be a point where a light bulb will go off at some point in this section, and you'll just be like, wow, this all makes complete sense, and it's actually pretty easy. You just got to get to that point. Just like your energy levels were on the table, these sublevels are also on the table as well. So you need to label these sublevels on your table. You're going to be referencing this a lot. So the S, P, D, and F can be found on your table. So these first 2 columns on the left, these here are your S sublevel, along with helium over here. All right, because he technically would fit in this spot right there. So those first 2 columns on the left, along with helium over here on the right, those are your S sublevels. The P is over here on the right side. This block here would be your P's. And then your D sublevel are all these elements here in the middle. These are all the D sublevel. And then these down here at the bottom These two rows are your Fs. So the periodic table is arranged nicely in these sublevels. Definitely label your table because you need to be able to reference this. So if you remember on the previous slide, we talked about the maximum number of electrons for each of these. I told you can use your table for this stuff if you know how to read it. So let's just say, for example, we look here in the S, all right? What's the maximum number of elements you could have in any row for an S? So if you look at this, let's just say the second row. What's the maximum number of elements you could have in the S? Well, 1, 2. Those are the only two there in the second row. What about the third row? It's just 1, 2. Same thing with the fourth, just 1, 2. If you remember back, what's the maximum number of electrons you could have for an S? Well, the answer was 2. All right. Look at the P section. We said the maximum number of electrons you could have in any P sublevel was 6. Well, count any row for a P. For the P's over here, it's 1, 2, 3, 4, 5, 6. Any row can only have at most 6 elements in the P. So this information, like I said, is visible on the table if you know how to use it. And eventually you get to a point where this will make complete sense. So you need to know where these sublevels are on your periodic table just by looking at it. We've already gone through the first two quantum numbers, so now we're at orbitals here. Orbitals are regions within a sublevel that can hold at most 2 electrons. So if you remember here, an energy level was an area outside of the nucleus where you're likely to find electrons. Sublevels were inside energy levels, and now orbitals are areas in a sublevel where you can have at most 2 electrons. Okay, so these electrons are in what we call an orbital pair. They're spinning in opposite directions. We'll talk about this more in a little bit. The numbers here go from -3 to +3, but the good news is you don't need to know about that. All right, we don't hold you accountable for the quantum numbers here for the orbitals, so you don't need to worry about that for this particular slide. But there's another piece of important information here. Each sublevel can have a different number of these orbitals. Think about it. Orbitals are areas that can hold at most 2 electrons. So each sublevel has a different number of orbitals. S's only have 1 orbital, P's have 3, D's have 5, and F's have 7. Again, you're probably thinking, oh my goodness, how am I going to remember this? Well, think about it. Each orbital can only have 2 electrons. At most, S can only hold 2 electrons. So S can only have 1 orbital because each orbital holds 2 electrons, which is the most that an S can have. Well, we said the maximum number of electrons that P could have was 6. So P only has 3 orbitals because each of those orbitals are going to hold 2, which would give you your maximum of 6, right? So all this does tie together. You can figure out the maximum number here of electrons just by taking the number of orbitals times 2. So for example, F has 7 orbitals, each holds 2, 7 times 2, F's hold 14 electrons. So this ties in with the information we already had talked about earlier here in this video. The last quantum number we're going to talk about here is the spin. And this is the last part here that kind of differentiates the electron itself. We said that these electrons are in these spinning pairs. Basically, one's going up and one's going down. It's almost like saying one electron's living upstairs and one electron's living downstairs. And when we do our orbital diagrams in a little bit, you'll see that we do show this opposite spinning in our diagrams. So there are 2 possible values for this, and this is not something major, but there's a +1/2, -1/2, and they're just indicating that these electrons have opposite spins. So we really hold you accountable for the principal quantum number and the azimuthal quantum number in terms of knowing the numbers, but for the orbital and for the spin, we don't really hold you accountable for knowing those numbers here. So we will see this opposite spin when we do our orbital diagrams in a little bit. So now we've seen all 4 quantum numbers. And again, all we're trying to do is get more information about the location of an electron. I want to just do a quick summary here to hopefully bring this all together. So the first thing we talked about here were the energy levels. Okay, and we said these energy levels were areas outside of the nucleus where you're likely to find electrons. And we tied this in with the letter N, and we also said this related to the principal quantum number. All right, so all this is the area outside the nucleus where you're likely to find electrons. Now what we're trying to do is we're basically like zooming in. Okay, we're trying to find where these electrons are located. So this is kind of the area outside the nucleus. So then we zoomed in and we said, well, a sublevel is an area inside an energy level where you're likely to find electrons. So we said that these were, S, P, D, or F, and we talked about this in terms of the azimuthal quantum number, or L. So this is just areas inside of an energy level. We're zooming in. And then we said, okay, well, inside a sublevel is an orbital. And orbitals have at max 2 electrons in each. So orbitals are areas inside a sublevel. Again, we're just zooming in, where you can have at most 2 electrons. And then the last thing we talked about was the spin. And this basically tells us which electron it is. It's like basically you get to the point where you're identifying the electron. So the way I like to think about this is that this energy level kind of represents the town that the electron lives in. The sublevel zooms in further and basically says, okay, this is the street now that the electron lives on. The orbital is kind of saying like, okay, this is the house that the electron lives in. And then the spin is basically saying, okay, this is the exact location, like top floor or bottom floor. All right, so you have kind of 2 electrons in each house. One lives upstairs and one lives downstairs. So all we did was kind of just narrow our focus and get more and more zoomed in here to hopefully find out some more information about an electron. This slide provides a summary about the different energy levels and sublevels, and all this information can be found on your periodic table. For example, if you were in the first energy level where n equals 1, this would be the first row, because remember, energy levels are your rows. If you're in your first row of your periodic table, all right, how many sublevels do you see? If you look at your labeled on your table, the first row, the only sublevel, the S, P, D, or F that you have labeled is just S. So there's only one sublevel in the first energy level. The number of orbitals there, all right, is just 1. Remember, S can only have 1 orbital. You could figure out the number of orbitals for any energy level just by doing n squared. If you wanted to know the number of orbitals for, say, the second energy level, just do 2 squared, and it's 4. You know the number of orbitals for any energy level. And then the maximum number of electrons that you can have in the first energy level is 2. Remember, we already talked about 2n squared gives you the maximum number of electrons in any energy level where n is your energy level. All right, this is visible on your table. Think about this. If you count how many elements are in the first energy level on your table, there's just hydrogen and helium. There's 2. Well, what if you look at the second energy level? All right, so now you're in the second row. There's S's and P's. You have S's on the left. You have your P's now on the right for the second row. The maximum number of orbitals you can have is n squared, or 4. And the maximum number of electrons you can have, 2n squared, is 8. If you count the number of elements on the second row of your periodic table, you will see that there are 8. So this really does tie in with the periodic table. If you're not quite seeing it yet, you will see this by the end of this section. A light bulb will go off, and this all kind of ties together here as we work through these electron configurations. So all that information was basically like background information, trying to get us now to electron configurations and being able to do electron configuration. All electron configurations is they're going to show you how these electrons are arranged in the orbitals here for an atom. And there are 3 different ways to do this. So the first way that we're going to do in this video is called orbital diagrams. It uses boxes and arrows. All right, boxes and arrows here. Boxes represent the orbitals. The arrows will represent electrons. And then SPDF notation is kind of a shorter version of orbital diagram, and then kernel notation is an even shorter version of SPDF. So it kind of, you start with the longest one here, and then the electron configurations get easier as you go. So once you have this first one, it pretty much just gets easier from here. So we're going to work on orbital diagrams eventually in this video. In order to do any electron configuration, there are 3 rules that must be followed. And we will apply these rules as you're doing electron configurations here. You have to follow them. So the off-bow principle says that you have to add electrons one at a time to orbitals of the lowest energy first. So you always have to start with the lowest energy. We already talked about the energy levels here, that the first energy level was the lowest in energy, and as you went up to 7, you got higher in energy. We already said that S's were lower in energy than P, which were lower than D, and so on. So off-bow says you add electrons to the lowest energy first. The Pauli exclusion principle says that electrons must have opposite spins, and you can only have a max of 2 electrons for every orbital. We already kind of talked about how there can only be 2 electrons for every orbital, and the reason this is because the electron must have a set of 4 different quantum numbers. Each electron has its own set of 4 different quantum numbers. It's kind of like you want to think about like each electron has its own address. So if, a particular electron lived at, 2319 and another electron lived at 2320. Okay, so it's just kind of like the address of a house. These electrons need a set of 4 different quantum numbers. And then Hund's rule says each orbital in the sublevel must have 1 electron before you would pair them up. So I want to show you a little bit more about what this actually means. So we represent orbitals here with boxes. If I wanted to draw a P sublevels have 3 orbitals, if you remember from earlier in the notes. So by me drawing this like this, 3 boxes, that represents a P sublevel, all right? What Hund's rule says here is each of these orbitals, so each of these boxes has to have 1 electron before you would ever pair them up. So you could put at most 2 electrons in each one of these boxes. So if I had 3 electrons, let's say, Hund's rule says I have to put 1 in the first box, 1 in the second, and then 1 in the third, because I have to have 1 in each orbital. All right, we draw electrons here with these like half arrows. Well, what if I had a 4th electron in this P sublevel? Then I could go back and pair up. Well, what if there was a 5th? Then I could add 1 to that box and so on. All right, so Hund's rule basically says you have to have 1 in each orbital before you would pair up. So basically, you could not have a P sublevel looking like this. If you had 2 electrons, you could not have them both in the first box because you need to put 1 in each of the boxes before you would ever pair up. So this would not be acceptable. All right, so you got to follow these rules. You need to know them and you need to use them. Here are the steps for doing an orbital diagram. I want to give them to you so you can see them, but you're just going to get to a point here. We're going to do examples, and you need to know how to do these orbital diagrams, and you'll just know how to do them without looking at these steps. But I think seeing the steps first is a good start here. So we use boxes to represent orbitals and arrows to represent electrons. When we're talking about orbitals, you need to know that the boxes represent the orbitals and the arrows represent electrons. Then you need to find the number of electrons for the element you're doing the orbital diagram for. Well, we know how to do this. We determined the number of protons, neutrons, and electrons already in previous notes, so this shouldn't be too bad. And then basically, you have to start with the lowest energy level first, always. So you always start with n equals 1. I'll show you how to do this. Again, you're going to use your table and pretty much here. You'll write down all your sublevels, and then you'll follow all your rules. You have to pay attention to that you can only have the maximum of 2 electrons per orbital. You have to have the correct number of orbitals for each of the sublevels, and so on. So we'll see all this when we do our orbital diagrams. And again, the periodic table will help you. If you are looking at your periodic table while you're doing this and tracing it, you'll see that this is actually pretty easy. I want to point this out to you on a periodic table so you can see what we mean by tracing the table. So the rule said you always start with the lowest energy first. The lowest energy first is always going to start in the first row. All right, you're always going to start every single time with the first row, first element, which is always going to be element number 1, hydrogen. And then what happens is you just literally follow your table as you go from element number 1, 2, 3, 4, so on. So you always start every single one of these orbital diagrams, every single one of these electron configurations, you start with element number 1. And then you just cruise over to the right to element number 2. Well, after element number 2 comes element number 3, and then 4. And you just keep cruising. As the atomic number increases, that's how you go, and that's how you follow your periodic table here. So every single time we do this, we're going to pick an element, we're going to start here with hydrogen, and we're just going to keep moving left to right, following the increasing atomic number until we get to the element that we are trying to do the orbital diagram or electron configuration for. For our first example, we are going to draw the orbital diagram here for lithium. Okay, so we already said that we're going to use boxes to represent orbitals and arrows to represent electrons. So we need to know here the number of electrons for lithium. So if you look up lithium on your periodic table, lithium has 3 electrons. So what that means is if we're going to use arrows to represent electrons, our orbital diagram needs to have 3 arrows in it, no more, no less. Okay, so if you have out your periodic table, which I strongly urge you to have out your periodic table, okay, your rules always say, Aufbau says, start with the lowest energy first. So you always start with element number 1. That would be the first energy level. That would be the lowest energy first. All right, you increase in energy as you go from 1 to 7. So you start with the very first element, hydrogen. If you were at hydrogen, what energy level are you in? All right, so think about that. I said, what energy level are you in? It's basically saying what row, what number is there on the left side of your periodic table? Well, it's number 1. All right, what sub-level are you in? If you're at hydrogen, what letter do you have labeled for hydrogen, S, P, D, or F? Well, you should have labeled your table with an S. So you're starting in the 1s. So now my question is going to be, how many orbitals would you draw for an S? S's have always 1 orbital, so you would always draw 1 box. Again, just for your reference here, S's have 1 orbital, P's have 3 orbitals, D's have 5 orbitals, and F's have 7 orbitals. So that's something that you just got to get to a point where you know that. Remember, each orbital can have at most 2 electrons. All right, so if I fill this box with 2 electrons, am I going to be over my number of total electrons I need? Well, no, because I need 3 total electrons here. So I draw 1 electron going up and the other going down in the box. Those arrows represent the electrons. And I know it looks kind of weird. Basically, you don't have to write the other part of the arrow. Some people always want to. Basically, they allow you just to write it like that because it saves kind of, picking up your pencil and going back and doing the other side of it. So those arrows here, they represent electrons. So right now, I have 2 electrons in the 1s. So I label this 1s2. It's not squared, it's just 1s2. That superscript is telling you how many electrons or how many arrows you drew in that orbital. All right, so by drawing those 2 arrows, what that's saying is if you look at your periodic table, the very first arrow here represents element number 1, or hydrogen. All right, this second arrow represents element number 2, or helium. All right, so after element number 2 on your table, look at your table, comes element number 3. Find element number 3. Okay, you're at lithium on your table. So if I ask you this question now, what energy level are you in if you're at lithium? Well, now you're in the second energy level. Those numbers on the left side of your table are your energy levels. So now you're in the second energy level. Well, if you're at lithium, what sublevel do you have labeled for lithium? Well, you have it labeled as S. How many orbitals do you draw for any S? Well, you draw one orbital, so one box. And at most, this could have 2 electrons in it. If I draw 2, though, I'm going to be at 4. I only have one more electron left to get to 3, so I just draw one arrow going up. And you would typically draw up before you go down. And I would label this 2s1. And people might say, well, you're missing one. Well, yeah, because I only need 3 total electrons here. If you count your arrows, you have 1, 2, 3. And that's what you needed. You needed 3 electrons here. The arrows represent the electrons. If you total up your superscript numbers here, 2 plus 1, you get 3. Those are your 3 electrons. So this would be the orbital diagram for lithium. Right here, this would be the correct orbital diagram. We started pretty easy, but that's the basic gist. You always start on your table with element number 1, and you just keep tracing along until you get to the element that you're trying to do the orbital diagram for. Now let's try to do the orbital diagram for silicon here. So silicon is going to be Si, and it has 14 electrons. So that means we have a little bit more work to do here. It's not going to be as simple as the last one, but it's still, pretty easy. These all basically go the same way. So just like before, you always start with the lowest energy level according to Huns. So you always start with element number 1 on your periodic table. So hydrogen. If you're at hydrogen, what energy level, what row are you in? You're in the first row. What sublevel do you have labeled on your table for hydrogen? So SP, D, or F, you have it labeled as S. S's always get 1 orbital, so 1 box. At most, every S could hold 2 electrons according to Pauli exclusion principle. So this would hold 1 going up, 1 going down. All right, holds at most 2 opposite spins here so that they have a different address. And we would label this 1s2. By drawing those 2 electrons, that represents element number 1, which is hydrogen, and element number 2, which is helium. So now you're at element number 3. Okay, you're just tracing along your table, moving left to right, following your atomic number, essentially. So now if you're at element number 3, lithium, what energy level are you now in? Well, now you're in the second row, so you're in the second energy level. What sublevel are you in if you're at lithium? Well, it's labeled S. S's get 1 orbital, so 1 box. At most, every S could hold 2. If I draw 2 in here, I'm not going to be at or over 14. So I'm just going to fill it, 1 going up, 1 going down, and I'm going to label this 2s2 because there's 2 electrons in that box. So now you have 4 total arrows. All right, so that means you're good through element number 4. By drawing in this arrow here, that would be the 3rd element, and this arrow here, that would be the 4th element. So you're good through element number 4. So on your table, you are filled up through beryllium. After element 4, cruise over to the right. Now you're at element number 5. What energy level are you in if you're at element number 5 or boron? What energy level? What row? You're still in the 2, but now you're no longer in the S. You're in the P sublevel. Your table has the P block labeled here. How many orbitals does a P have? P's have 3 orbitals. Okay? Each orbital can hold at most 2 electrons for a total of 6. If I draw all 6 in here, am I going to be at 14? No. So it's going to be filled. Hund's rule says 1 in every box before you're forced to pair, and you're going to be totally filled here. So you're going to have 6 total in the 2p. Okay? So if you count your electrons now, these 6 now put you at a total of 10 electrons. So that means you are good through element number 10 or neon. Basically, every one of these you added. This was the 5th one, this was the 6th, 7th, 8th, 9th, 10th. So now you're good through element number 10 or neon. So after number 10, trace your table, you're at number 11. What energy level are you in? Well, now you're in the third energy level or the third row. What sublevel are you in if you're at element number 11 or sodium? Well, that's the S again. S's get one orbital, one box. At most, it could hold two. It's going to be filled, one going up, one going down, and it's going to be 3s2. That takes care of element number 11 and element number 12. This would be 11, is your 11th arrow. This is your 12th arrow. So that means you are now at element number 13. So if you're at aluminum, what energy level are you in? You're still in the third, okay? But now you're in the P sublevel. P's get 3 orbitals. Again, that's just something you need to get used to. At most, you could have 2 in every orbital for a total of 6, but we only have how many electrons left? We only have 2 more electrons left till we hit 14. We're not just going to fill this up because there's only 2 more electrons left. So Hund's rule says 1 in each before you're forced to pair. Well, there's only 2 left, so this is going to be 3p2. That last orbital is not going to get anything, and these two are both going to be unpaired. So if you count up all your arrows or you total up all your superscripts here, it equals 14. You're done. And that's basically how you do an electron configuration for any element. Start at element number 1 and just keep tracing along the table using your energy level and sublevels until you get to the element you're doing. So I want you to try the orbital diagram for potassium here on your own. See what you can do here. Pause the video, do it, and then come back and I'll have the answer completely there for you. So pause the video and try this. So hopefully this is the answer you got for potassium. When you trace along your periodic table, you end with 4s1. Potassium is in the fourth energy level there. It's in the S, and there's just 1 till it gets to potassium. Again, if you count up all your electrons or total up all your superscripts, they should equal 19. I think hopefully some of you are starting to see this connection here, how you just literally use your periodic table every single time. And pretty much it does repeat for every single element. You notice you always start with 1s2 and then 2s2 and so on. It just repeats, and you just keep tracing along your periodic table. One more example here. I want to show you this one because it does have a little bit of a difference in it. One other thing I want to point out. So we're going to do this for iron. So Fe here with 26 electrons. So yes, that means you do have to show 26 arrows in your picture. But we always start at element number 1 and trace your way. Feel free if you feel like you got this to kind of, do this on your own and skip ahead. But there is going to be a slight difference here that we didn't talk about yet. So we would always start at element number 1 or hydrogen. So we're going to be at 1s2 here. All right. 1 up, 1 down, 1 orbital for an S. After you fill numbers 1 and 2, now you're at element number 3 or lithium. You'd be in the second energy level. You're still in S. S's get 1 orbital and it's going to be filled. So 2s2. That takes care of electrons up through element number 4. So after 4 comes 5, boron. So now you're in the second energy level, but this time you're in the P sublevel. P's get 3 orbitals, at most 2 in each. It's going to be filled. It's going to be 2p6. So that takes you through element number 10. After element number 10 comes number 11 or sodium. You're in the third energy level. You're still in the S. S's get 1 box, 1 orbital, 1 up, 1 down. At most 2 electrons. It's going to be filled. So that takes care of elements number 11 and 12. So now you're at element number 13. So you're still in the third energy level. Now you're in the P sublevel. P's get 3 orbitals, 1 up, 1 down in each for a total of 6. All right, that takes care of up through element number 18. So we still have a few more to go. So after element 18 comes number 19. You're at potassium. So now you're in the fourth energy level. You're in the S sublevel. S's get 1 box, 1 orbital, 1 up, 1 down, at most 2 electrons. It's going to be 4s2. So that takes you up through element number 20, or calcium. So now we're ready to move on to element number 21. So if you look at your periodic table, once you hit element number 21, you're now in the D sublevel. All right. And something very important to point out about the D sublevel is that they are one row behind. So even though you're in the fourth row or the fourth energy level, when you get to number 21, you're not in the 4D. You're in the 3D. And that's just something you got to get used to. The D sublevels are one row off. If you're in the fourth row, you're in the 3D. If you're in the fifth row, you're in the 4D, and so on. So we are not in the 4D here. After 4s2 comes 3D. Ds get 5 orbitals. So we got to draw 5 boxes for a D. All right, at most you could have 2 in each for a total of 10. But we only have 6 more electrons left until we reach our total of 26. So Hund's rule says 1 in each before you're forced to pair up. So that first orbital there is going to have 2, and all the rest are just going to have 1. And this is going to be 3D6. Okay, so just something you got to get used to. The D sublevels are off by 1. So pay attention to that. Even though you're in the fourth row, you're in the 3D. But pretty much if you can understand that and you can trace this on your table, you could do any orbital diagram I would give you.